So on the problem set itself, so I would like to first prepare the problem set and then tell you whether this is going to be something that we do on Thursday or not. Also because you don't have the material, I think I didn't upload the slides from panel data. Yes, so I would like you to actually see the slides before coming to the problem set. That's why I think we are going to postpone this problem set to next week. I don't know when, because I need to see. It would be best to do it on Monday. So this is something that I need to check also regarding the availability of the lab. So I will let you know, of course, always in the objective to give you the instruments to do it with my class and online, of course. And also in terms of the exam, since this is the first time that so you don't have maybe colleagues who did this exam with me from the previous years, and actually it seems that this course has a different professor year by year. I don't know whether next year I will have it or not. But I would like to do a mock exam before the end of the course. So probably on the last week, because we are going to do class until the end of the month, because we need to do 3 classes that we didn't do, which I canceled. So that's why we need to also cover the last week of May. And probably during one of the classes, one of the lectures will be a mock exam where I give you a simulation of an exam that I can give you then on of course, in June or July. It's just a simulation, of course, it's not the exam. But then you can do it during so I will give you 1 hour. Of course, you can come to me, ask me whether it's best to proceed in one way or another, if I like, for example, a formula or also some text, so maybe you have some concerns about that. And also in terms of structure of the exam, so you are prepared. This is something that I think it's useful for you, and it's useful for studying better, to have everything more focused and easier. And also it's something, since I remember that when I gave you the exam dates, you were concerned, worried about whether basically to pass this exam on the first time. Of course, my aim is to let you pass the exam if you study, no? So just I will give you this mock exam, and I think this makes everything easier for both of us. Okay, so today we are gonna, in also in terms of problem, I think, so I decided what I'm gonna cover with you. So we're gonna do this binary dependent variable, which are probably the logic and probably models. These are models where the dependent variable is not anymore continuous, but is a binary variable. So until now, we've seen the possibility that one of the regressors or all the regressors are dummy variables, and we've seen that this doesn't really change anything in terms of estimation tools. These were still multiple regression models with the standard tools estimated by OLS. We can do inference about those coefficients with single coefficient hypothesis testing. We know how to build or joint hypothesis testing. We know how to compute standard errors. So this is something that we know of very well. But things get a little bit more complex when the dependent variable is a binary variable. So a variable which takes on 0 or 1, 2 possible outcomes. And we will see this case. And whenever we have this case, we need to use nonlinear regression models. So also, this is something that we did, no? How to address nonlinearity, transforming this model in terms of linear models to be estimated by ULS. In this case, we need to actually go through nonlinear models, so where the functional form is nonlinear, and these models cannot be estimated by our methods, so the methods that we know of. So this is why we need to introduce nonlinear regression estimation methods. And also there are some differences that we need to address. So this is what we are gonna do today. Then so it depends, of course, on what I decide to do in terms of problem set. But next time we're gonna cover regressions with instrumental variables. And actually, just one thing that I want to tell you. So these models with binary dependent variables are really very much used for inertial econometrics. So whether for example, a vaccine increases or reduces the probability of getting this virus. So this is, for example, one application. So whenever I'm looking at the probability as the dependent, so we will see that basically our models where we have a binary dependent variable could be, so are interpreted in terms of probability of that the variable is equal to 1. So the variable could be equal to 0 or equal to 1. The interpretation of these models change, okay? And then the interpretation basically turns in terms of probability that this variable is equal to 1. So whenever I want to assess whether some treatment, which could be, for example, the event of being vaccinated, has an effect on the probability of being successful or not in terms of something. So, for example, the probability of getting or not the virus, this is something that we use. And if you can, as you can understand, this is something that in health econometrics is very much done. For example, a colleague of mine is a doctor. She's conducting a research, and she wants to estimate whether some treatments that they are assigning to some patients are actually successful in reducing the probability of doing something. This is what they do. So this is one of the main regression models that you're gonna use. You're going to use in the case in which you want to, of course, still apply quantitative methods to your research or to your questions. Okay, so later on we will do instrumental variables, and then we will do experiments and non-experiments. And with that chapter, we're going to close this the program. Okay. And then I will invite 3 people to give you seminars. One of them very likely will come to apply these logic and probability models, so these models, to one phenomenon in a more advanced framework. So we need to just be ready for that, to see basically the intuition. So we are covering the basics, of course, so they are coming to do something more advanced. Also, another friend of mine will come to do something still more advanced, but don't worry, these are 3 applications that I would like to show you. They will not be in your exam, but please come, I think they are interesting, okay? Okay, so for today we are gonna cover this possibility to have a dependent variable which is a dummy variable equal to 1 or equal to 0, whether we are whether some event is successful or not. And the first model that we are going to see is a linear probability model. So still a model which is linear in the regression, in the regressors. Then we're going to see a non-linear probability models, because since we can interpret these models in terms of probabilities, non-linear probability models are more are better for representing probabilities, and these are the probit models and the logic models. And then we are going to see, as I told you, how estimation and inference change when we have these kind of models, and we are going to introduce maximum likelihood methods. This is the method that Stata uses, and in a very general way, so I'm not going too much into detail, but also in terms of measures of fit, actually something changes, and so we don't have anymore the adjusted R square, but we have this another measure which is called pseudo R square. So we're going to do that also to being able to interpret what we see in terms of standard output. So until now we have seen test scores as a dependent variable. Okay, so the variable that we want to explain in terms of regressors, we've seen in our examples, test scores, earnings, traffic fatality rates. So these are continuous variables. Okay, so they can take on a continuous set of values. So now we're going to see the case in which y is binary, and this could be, for example, the case in which y, so in the case in which the entity, so we are back to the case of cross-sectional data, okay? So we don't have any more the t dimension. So this is the case in which the I entity gets into college or not, okay? So in the case in which the I entity, the I individual gets into college, y is equal to 1. In the case in which the I entity does not enter into the college, then y is equal to 0. And then we want to explain whether y is equal to 1 or equal to 0 in terms of some regressors, which it could be high school grades, parental income, demographic variables. So we want to explain whether y is equal to 1 or not. In other terms, just to be used to get used to this idea, we want to explain the probability that y is equal to 1 or not, the probability of getting into the college in terms of parental income, high school grades, demographic variables. So, for example, is your parental income increasing the probability that you get into the college? So this is the question that you are actually asked to answer. Okay. And also another example could be whether this I entity smokes or not. So in the case in which I smokes, the dependent variable is equal to 1. In the case in which I does not smoke, then the dependent variable is equal to 0. And then we want to explain the probability of smoking or not. So whether y is equal to 1 or equal to 0 in terms of what the policy does. So the cigarette tax rates, income. So maybe there could be a theory which tells us that people who so actually there could be two theories. So the first one, that people who are actually who earn more, whose income is higher, they of course can buy those cigarettes and they maybe smoke more. But there could be also another theory which tells us that people who with a higher income, maybe they perceive that by smoking they will get some negative effects in terms of health, or maybe there are cultural attitudes which are linked to, correlated to income, which will lead to actually decrease or at least not smoking. Okay, so we are asked to estimate the effect of some regressors on the probability that this y variable is equal to 1 or equal to 0. This is the difference. Okay, so y is our dependent variable, and this could be equal to 1. The other example that we are going to cover actually now is the possibility to being accepted for a mortgage application. So y is equal to 1 in the case in which this mortgage is accepted, mortgage application to a loan officer, bank loan officer is accepted, and is equal to 0 whether in the case in which this mortgage is not accepted. So basically we are gonna assess the evidence of discrimination in the mortgage market. So which are the variables? Income, house characteristics, marital status, and so on, which affects whether my application for a loan is accepted or not. So this is the kind of questions that we want to answer. And now we will see the methods to do that. So let's first take this last example. So, and we know from the data that most individuals who want to, of course, buy a house need to apply for a mortgage. Not all mortgage applications are approved. So the question is what determines whether this application is accepted or not. And we take data from single family mortgages in one specific time period. So that's why we are in the first section, as I mentioned, in Boston. Okay. And data collected from this database of home mortgage disclosure account. We have 2,380 observations, and then here we have the dependent variable y equal to 1 whether the mortgage is denied, and y is equal to 0 whether the mortgage is accepted. And then we have some independent variables which probably are likely to determine this whether this y is equal to 1 or 0. So y is in this case this variable deny, called that we label deny. This is equal to 1, as I said, when the mortgage is denied with some standard deviation. Okay. Then we want to explain this probability in terms of this measure, which we assume is important, which is the fraction, the ratio between anticipated monthly loan payments over the monthly income. Okay, so whether you are paying for this mortgage loan too much in terms of your income, so maybe the bank assumes that you are not actually very able to afford the loan, okay, the mortgage, if the loan payments are too high with respect to what you get monthly from your job, okay? So if I apply for a loan and I'm assumed to pay a very large fraction of my monthly income, maybe the bank could think that I cannot really afford this mortgage loan. No? If I, for example, my brother earns more than me, for sure, and for sure is so a bank would be led to think that it can is more reliable as a client, no, with respect to me. So this variable could be important to explain whether this bank loan officer accepts or not this application. And then this book also assesses whether the race is important or not. Okay, and this is also dummy variable. And then the question is, does the payment to income ratio, so this variable, affect whether or not the mortgage application is denied or accepted? What can we do? We can just use the methods that we know. So we just regress the dependent variable, which is a dummy variable, And then this variable that we believe is important for explaining why. And then this is for the standard errors. So we actually didn't introduce anything new. This is a linear model with a dependent variable. Nothing. This is actually called the linear probability model. Why? Because this is linear in the independent variables, so this is linear in the regressor, and probability. This is a probability model because we can interpret this model in terms of probability, and this is something that we will see. So now the question is, we didn't introduce anything new, we just used a dependent variable, which is a dummy variable, and we got this coefficient. This is the coefficient, this is beta 1, okay? This is the coefficient ahead of the payment to income ratio. And then that, of course, is beta 0. Then the question is, how should we interpret this coefficient? How should we interpret the regression population line? No, beta 0 plus beta 1 x. How should we interpret the predicted outcomes? So all the tools that we actually know how to interpret in a normal framework where we have a continuous dependent variable, how those apply to this case. It's just a matter of interpretation. So we can do that, we use the standard tools, but then we need to be careful about the interpretation. So here we basically, what we did is just a linear model in X. And then the difference here is of course about Y, and we can interpret this model in terms of regression function. So what actually this model is in terms of a conditional probability model. So the regression function is beta 0 plus beta 1x. You remember that is the regression line. That is could be interpreted as a conditional probability model, where the predicted value of Y is actually the predicted probability that Y is equal to 1 given X. This is something that I'm telling you before proving that, okay? So don't be scared. But the idea is just that instead of having Y hat equal to beta 0 hat plus beta 1 hat X, so this is the predicted Y, okay? Here, Y hat is the predicted probability that Y is equal to 1. So this is the interpretation. So when I replace, if I ask you to, given this estimation, okay, given this beta 0 and beta 1 estimated, to give me Y hat, so deny hat. So this is a question that I asked you many times in the case in which the dependent variable was continuous. And the answer is that is the predicted value for average earnings. Okay. Here, the interpretation is different. If I ask you to actually give me the predicted Y, that is not the average Y, but that is the probability of Y equal to 1. So that is the probability, the average probability of having the mortgage application denied. So we interpret the predicted value of Y as the probability that Y is equal to 1. Interpret this question with coefficient. Yes, so this is something that we are going to do. So I was going there. So basically, in terms of coefficient, if Y hat is the probability, the predicted probability that Y is equal to 1 on average, then 0.6 is the change in the probability of Y equal to 1. So an increase in the payment to income ratio of 1 unit leads to an increase in the probability of having the mortgage application denied by 0.6. So this is the interpretation that we assign. So once we understand that In this case, the interpretation of y hat and the regression line is done by using basically a probability model, okay, a conditional probability model. Then interpretation of beta 1 is straightforward. This is the change in the predicted probability that 1 is equal to 1 when x increases by 1 unit. Okay, if we add another regressor there, of course, this was conditional controlling for the other regressors. So this is just to give you an intuition. Now we will see why we can interpret the predicted value of y as the probability that y is equal to 1. So this is actually the key point that we need to understand. Once we understand that, then it's straightforward to see why an increase in x leads to a change, can be interpreted in, beta 1 can be interpreted as the effect of increasing x on the probability that y is equal to 1. So let's see, first of all, this figure where we have the x, of course, the regressor here on the x-axis. This is the payment to income ratio, which we believe would explain whether the mortgage application is accepted or denied. With this is a scatter plot. The only difference is that now on the y-axis, we don't have anymore a continuous variable, but we have a discrete variable with taking on only two values. On the x-axis, we still have, of course, a continuous variable. Okay, so that's why we have values just here and here. So y could be equal to 0, mortgage application is accepted, y is equal to 1, denied. Okay, and we already see from this scatter plot that there is a relationship. Okay, so if you don't see the line, you can actually already see that for low payment to income ratio, if I'm paying just a small fraction of what I earn, the probability of getting the mortgage application accepted is higher. So the probability of being denied is actually low. Okay. So for those who have a payment to income ratio which is low, for example, my brother, probably, it's very unlikely that he will be denied in terms of course of mortgage application. Those who have a higher payment to income ratio, which could be, for example, my case, they probably are those who are denied. Okay, so we already see that there is the payment to income ratio and whether you are denied, your application is denied. Okay, so this
excuse me, so the payment
when we estimate this model where we didn't do nothing different than regressing the dependent variable in terms of the regressor, the payment to income ratio. In this case, we have an estimate for beta 0 and an estimate for beta 1. These are the standard errors. Okay, so nothing really new. When we do that, we are basically fitting a regression line which is linear. And then the question is, again, how do we interpret this regression line? Because, for example, if I didn't know the answer, I could be led to, for example, say, so when x is equal to 0.4, when the payment to income ratio is 0.4, what does it mean that y is equal to 0.4 or something similar? What does it mean? Y could be equal to 0 or equal to 1. Is equal to 0.4. This variable, which could only take values 0 or 1, is actually estimated to be 0.4. This is the predicted value y, no? You remember. So all these values on the regression line, on the estimated regression line, is the predicted value for y for each x. So then I would face this challenge to understand what this model actually, what this regression line means, what is the meaning of the interpretation of the predicted value, and then from that we understand the meaning of beta 1. Okay, and the answer is this 0.4, y is equal to 0.4 is the probability that y is equal to 1. So when the payment to income ratio is equal to 0.4, the probability that you are that your application is denied is 0.4. So this is the probability that the y is equal to 1. So this means that if you have many people who with the payment income ratio equal to 1, also if you remember you have done of course some probability, right? Or I don't know, but when you do statistics, you always learn about the basic definition of probability, and that is the frequency of some event, basically. The relative frequency of some event. So this, in terms of interpretation, using the same example, this also means that when you have many people with the payment income ratio equal to 0.4, 40% of them are denied by using the definition of probability. Okay? So let's see why is that. So now we are going, so the answer is this one. So this is how we interpret the predicted y. And then beta 1 is the change in the predicted y, in the probability that y is equal to 1 when x increased by 1 unit. Okay? But this follows the interpretation of the regression line and the predicted value for y. So why does this happen? Because I told you so, or because we can actually prove that. Of course, this the second case is so we can, if we write down the conditional expectation of y given x for each entity. So this is the regression population line. Okay, so the conditional expectation of y given x is the regression line in population. If we actually replace with y the model, where is the model? This was the model for y, beta 0 plus beta 1 xi plus y. And we apply the first least square assumption for which the conditional expectation of u given x is equal to 0. This is the conditional mean zero assumption for u. This tells us that the errors are correlated to the regressors. And if this is not valid, then we have the omitted variable bias. This is the most important assumption that we need to make for well-less models. So if this holds, then the conditional mean of y, which is our regression line, is equal to beta 0 plus beta 1 x. This is nothing new. So this is something that we already know of. But then we can also write the conditional mean of y given x as y, so this is y equal to 1 times the probability that y is equal to 1 given x, plus y is equal to 0 times the probability that 1 is equal to 0 given x. Okay, so we have just two values for y. The conditional mean of y is, of course, if we do not take into account x, it's the same, but here we have a regressor, so we need to do that. But in general, the mean, if we actually computed the mean, this is something that we did, I think, when we did the review at the beginning. So the expected value of y is actually the probability that, So when y is equal to 0, so this is in the case in which y is equal to 0 and equal to 1, it is 0 times the probability that y is equal to 0 plus 1 times the probability that y is equal to 1. Okay? In other terms, this is the sum in terms of y equal to the small y times the probability that y is equal to 1. This is the expected value. So when we did the computation of moments for a probability distribution, remember, for a continuous variable, this is what happens for a continuous variable, this is what happens when we have a dummy variable. This is just the mean of y, the expected value of y, nothing new. Since we have a regression model, then we need to introduce the idea that of conditional expectation with respect to the regression. That's why we need to introduce conditional probabilities. And this is what we see here. So this is y equal to 1 times the probability that 1 is equal. So this is just the conditional expectation of y. We didn't apply anything new. We just applied the formula for the expected value to the case of a binary variable plus the idea that we need to condition on the regressor because now we have a regression model. Okay. Okay, then if we just solve this, then 0 by the probability that y is equal to 0, 0 times something is 0, then we are left with the probability that y is equal to 1 given x. So the conditional expectation of y given x is equal to the probability that y is equal to 1 given x. That's it. The conditional expectation is the regression line. Is the predicted value of y given x. If this is equal to the probability that y is equal to 1, then this is the interpretation given x. This is the interpretation that we wanted to prove was actually there. Okay? So the regression line in population in this case, but also what we estimate, the predicted y is the probability, should be interpreted as the probability of y equals to 1 given x. So when x is equal to 0.5, what is the probability that y is equal to 1? Okay. So this is a matter of interpretation, and then given that interpretation, beta I is the change, this is the first derivative, the partial derivative, is the change in the probability that y is equal to 1 given x when we increase x by 1. This is the partial derivative. The fact that we always said that beta 1 was the delta y over delta x. Okay? In this case, we have that beta is delta, the probability that y is equal to 1 given x over delta x. In terms of partial derivative, this is what we get. Okay? And then this is the interpretation, this is actually the answer to your question of this idea of the probability model to the example that we have seen. So when we estimate a linear probability model, so this is just a simple model where we use reg, the dependent variable, and then the dependent variable. We have this result, of course, applied to the data that the application that we are interested in. And this 0.6 was actually the coefficient which gives us the positive relationship. Okay? What is the interpretation of 0.6? Interpretation is that a change in the payment to income ratio by 1 unit is estimated to increase the probability that the mortgage application is denied by 0.6. Okay, so if I give you that type of table, the interpretation of beta 1 is this one. Then the question could be, what is the predicted probability of y of denying, so that the mortgage is denied when the payment to income ratio is equal to 0.3. So also visually, this is the question, this is the answer. Okay, the predicted probability when the payment to income ratio is equal to 0.3 is something around 0.2. 0.50. Okay, so this is done how? By using the regression model with the payment income ratio equal to 0.3, and this is the answer. This is the predicted probability of being denied when I have a payment to income ratio equal to 0.3. Okay. Another question could be, what is the effect of a change in the payment to income ratio by 0.1? So we have seen that if the change in the income ratio is equal to 1, then the effect is given by 0.6. If x increased by 1, the effect on the probability that y is equal to 1 is equal to 0.6. If x increases by 0.01, the effect is given by 0.06, which is 60%. Okay, so if the payment income ratio increases by 0.1, then the increase in the probability is by 6%. Indeed, if we compute the predicted, so here we compute the predicted value for y equal to 1 when x is equal to 0.3. Now we are computing the predicted value of y equal to 1 when x is equal to 0.4. We just use the regression model estimated with x equal to 0.4. We get 0.21. The difference between this and this is 6%. So by increasing x by 0.1, the effect is an increase in the probability of being denied by 6%. And this effect is constant over x. Why? Because we have a linear regression model. Okay, so the idea of the linear regression model always, not in this case, but just always, is that if we increase the x from 0.4 to 0.5, or if we increase x from 0.5 to 0.6, the effect on y is the same. Why? Because the slope of this curve is constant over x. If we had a quadratic model, for example, you remember when we had a polynomial which was quadratic, the effect depended on x. If we have a line with an increasing slope, then by increasing x, the effect on y increases. But in this case, we have a linear model, so by increasing x by a certain amount, the effect on y is the same whether we are here or whether we are here. Okay, so this is the definition of a linear model. This is a linear probability model. The difference is that just on the y predicted side, we have the probability that y is equal to 1. The rest is actually the same. Okay. Okay. So just to summarize this linear probability model, as you can see, this is not, I never used the idea of probability logic, so we still didn't use those models which are actually non-linear in the regressions. Those are non-linear probability models. So here we're still in the case of linear probability models. This model, the probability, the linear probability model models the probability that y is equal to 1 given x, and this is a linear function of x. So this is what we proved up to now. That the population regression function is the probability that y is equal to 1 given x, and that the population coefficient beta 1 is the change in the probability that 1 is equal to 1 by increasing x. Okay, which are the advantages of this method? This is very simple. Okay, so it's very simple. We have just a binary dependent variable. We use the reg common. We estimate this model. This is a linear model. We estimate this model by OLS. We use the standard assumptions for least square estimation that we know of, the 4 assumptions that we have done. These are all also for the linear probability model. We do inference as we are used to do for multiple regression, so hypothesis testing, standard errors, and so on. The only difference is that we need to be careful because in this case we always have heteroscedastic errors, so we always need to use the ROB after the common to get heteroscedastic robust heteroscedasticity robust standard errors, and also the measure of fit is different. But aside from that, everything is very easy. Which are the disadvantages of this easy model? The disadvantage is that is exactly what I told you, that the effect of a change in x is constant. The effect of a change in x on y is a constant over x. And this is an issue. And this comes from the assumption of linearity. Okay? Why is this an issue? Because this is something that I do not want. Because when I have a very high probability, when I have, for example, turn into the case of whether the payment to income ratio has an effect on whether I'm denied or not. If I have a very high payment to income ratio, this increases the probability of being denied, right? But we should have that when this payment to income ratio is high, the effect is very high, so for extreme values of this payment to income ratio, the effect on y should not be constant with respect to like a lower payment to income ratio, but should be very similar to just the previous payment to income ratio. So let's assume that I have a very high payment to income ratio, an extreme value, 0.9. So basically 90% of what I earn is goes into the loan payment. And maybe you have 89%. Okay. So the effect on the probability of being denied, this difference between me and you should actually be marginal, should be negligible. Because basically we have a too high payment to income ratio. The probability for us is basically equal to 1, should be equal to 1. So the difference between us should be very marginal, should be negligible. Instead, in the linear probability model, the difference between me and you has an effect on the probability of being denied equal to the difference between people who have, for example, a lower payment to income ratio. So, for example, I have a payment to income ratio equal to 0.9, and you have a payment to income ratio equal to 0.89. They have a payment to income ratio of 0.3 and 0.29. So the difference is 0.1, okay? 0.01. Okay, so the effect of the difference between me and you on y is the same as the effect on the difference between them. But actually, we are extreme values of the payment to income ratio. Our probability to get our application being denied should be equal to 1. And the difference between us should be, so the effect of this change of 0.01 on the probability of being denied should be almost equal to 0. And that effect should be higher. Okay? So here, the effect, so let's assume actually, the effect of a difference between around 0.6 and around 0.4, okay, is the same on y, is the same. Okay, this is because we have a linear probability model. But actually, what we want is a model which tells us that for reasonable values of x of the payment income ratio, a change in this regressor has a certain impact on the probability of being denied. But when when x is very large, when the payment to income ratio is very high, whether I have a payment to income ratio equal to 0.58 or 0.6 shouldn't really make a big difference as for lower x in terms of the probability. We would have the application just being denied. So I want a model, and the same for very low payment to income ratio. The probability of being denied here is equal to 0 because we can afford this payment because we have an high income and this payment is just a small fraction of this income. So the probability should be equal to 0. So whether my brother has a 0.2 income ratio or his girlfriend has a 0.21 income ratio shouldn't really play a big difference in terms of the probability of being denied or not. Okay, so we want a model which gives us the possibility to have small effects of a change in x on y here, and small effects of a change of x on y for very high values of the payment to income ratio. So for extreme values of x, we want that the effect on y is very small. So basically, we want a model which is nonlinear. So it depends on x whether a change in x has an effect, a smaller or a larger effect on y. And this actually depends. So the idea, so why don't we want a model which is linear? Because here we are modeling probabilities, and the probabilities go between 0 and 1. So there is a finite interval where these probabilities are actually could go. Okay, so if I have very low values of this payment to income ratio, the probability cannot be negative, okay, of being denied. The probability is still 0, so we have a limit there. And the same for very high payment to income ratio. So if I have a very high payment to income ratio, the probability of being denied is just 1. It's not that by increasing this payment to income ratio further above 0.6, the probability of being denied can increase above 1. The probability is something which takes value between 0 and 1. So that's why we want a model which displays, allows us to have smaller effects on and reasonable effects in the middle values for x. So this is, I hope that this was clear. So this was the disadvantage of a linear probability model. We have probabilities, those are constrained between 0 and 1, and this is the reason why linear probability models are not good, do not really fit the idea of modeling probabilities. And that's why we want non-linear probability models like the probit and the logit regression. And of course, then the idea of these models is to, so we will see, instead of having a line, we will have something with another shape, a non-linear shape. And this non-linear shape is done by, is basically produced by cumulative density functions. We will see that in a moment. But basically, the idea is that we want a probability that y is equal to 1 given x, which is the predicted y, the regression line, which is non-linearly increasing in x. Okay. Of course, we want something which is non-linear. Why? Because this probability is constrained between 0 and 1 for all x. And this requires using a non-linear functional form for the probability. So we, instead of having the probability of y is equal to 1 equal to beta 0 plus beta 1 x, which is linear, we have some functional form of this. So we have, instead of having a linear form, so the probability is not equal to beta 0 plus beta 1 x, this probability is equal to a function of z, a function of this equation, okay? Where this function is between 0 and 1. In the probit regression model, this function is actually equal, if you remember this phi of z, this was the cumulative density function for a standard normal probability distribution. Okay, so this is the cumulative density for CDF of a standard normal in of z, where z is this equation here of our multiple regression model. So this, in other terms, if you remember the cumulative density function, the definition of the cumulative density function, this is the probability that this z variable is below a certain value. No? And the only difference with the logic model is that instead of using the CDF of a standard normal, we use the CDF of a logistic function. So we just use different nonlinear functions in these two models. Okay, but the basic idea here is that we use a nonlinear function of our multiple regression model. And this nonlinear function is a standard normal in the probit case and a logistic function in the logic case. So basically here, by using the probit model, we basically produce what is called the AS-shaped regression model. So as you can see, again, here we have the payment to income ratio. There we have the y equal to 1 or equal to 0. And while before we had a line, now we have that for small payment to income ratio, by increasing the payment to income ratio, the effect on y is very low. Okay, if we pass from 0.2 to 0.21, the effect on y is negligible. And the same for very large values of the payment to income. So this is what we wanted. For extreme values of the payment to income ratio, the probability of y equal to 1 is either equal to 0 or equal to 1. Cannot be negative, cannot be above 1. Okay, and this is done by this nonlinear model where the function is the cumulative density function of a standard normal distribution. So we actually satisfied these two conditions that we wanted. So this is the intuition of what we wanted that we actually solved by using the probability model. But more in the detail, basically the probability regression model models the probability that y is equal to 1 using this phi of z, where z is in the with the application of just one regressor equal to beta 0 plus beta 1. This is a nonlinear function, okay, of z. So why is this useful? Because it's easy. This probability, so actually before it was easier, no? Because the probability of y was given by beta 0 plus beta 1x. Beta 0 and beta 1 is something that we can estimate. It's easy for us to estimate the probability of y equals to 1. This is what we did in this example here, no? This is the probability of y is equal to 1. We just replace x and we got the predicted value of 1. Now we need to, we in front of this we have this phi of this, okay? But this is not a big issue because we have the tables of the which allow us to compute the value for the cumulative density function at a certain z, okay, at a certain number for z. So if we want to compute, let's assume that we estimate beta 0 equal to -2, beta 1 equal to 3, and we have that x is equal to 0.4. We want to compute y hat. Okay, the predicted value of y when the payment to income ratio is equal to 0.4, and we have the estimate for beta 0 and beta 1. What do? We use the model, so beta 0 plus beta 1 x. Okay, and then we need to compute the cumulative density function, the value of the cumulative density function at this z equal to -2 plus 3 times 0, so which is -0. So you actually go to the tables of the standard normal distribution function, and you will get the value for the area underlying. You remember that this is the probability that z, so beta 0 plus beta 1 x, is below -0.8. This is the definition of the cumulative density function. Okay, this is what we got. Probability that z is below a certain level. In other terms, if you remember the lectures that we did at the beginning for our review of probability, we are estimating the area underlying a standard normal distribution when z is equal to -0.8. You go to the tables of the standard normal distribution and you get the answer to this question. This is the probability for your application, mortgage application, to be denied when your payment to income ratio is equal to 0.3 by using a probability model which is nonlinear over x. Why? Because we are modeling probabilities and the probabilities are constrained between 0 and 1. This is actually easy to do. Okay, this fits very well the idea of a nonlinear probability model, and it's easy to compute. How do we do that on STADA? With the linear probability model, we have to just use the reg because this was linear. Instead of using the regression common, we use the probit common, and then we just add the dependent variable, the binary dependent variable. Then we have the payment to income ratio, which is our address. We use robust heteroscedasticity, robust standard errors, and voila. This is beta 1. This is beta 0. And then the probability of being denied given the payment to income ratio is given by the value of the area underlying the standard normal distribution. Okay, the area underlying the standard normal distribution when Z is equal to this number. Okay, so here we have beta 0 estimated plus beta 1 estimated times X. And just one thing that I want to tell you, as you can see here, we have this log likelihood because this is a nonlinear model and this is not estimated by OLS. This is estimated by another method which is called maximum likelihood method. That's why you see that. And also we have a different R-square, different test statistics. So we are using different methods because while up to now we were able to recast everything in terms of multiple regression models which were linear. In all cases we have seen up to now, so all the, whenever we use interaction variables, polynomials, logarithms, also in the case of panel data, we were able to transform everything in terms of something that we could estimate by OLS. Now we are estimating something which with nonlinear methods. So we will see different tools. So that's why the advantages of the linear probability model was that we were using the same assumptions and the same tools to estimate and to do inference. Here we need to use different tools because this is a nonlinear model estimated nonlinearly. Okay. So basically, so this is the output of the estimation. So how we actually write down the output of this estimation, where the probability of being denied is equal to the area underlining this number here. We see that there is a positive coefficient. So this is actually confirmed. The standard errors have the standard, the normal, the usual interpretation, and the predicted probabilities for certain values of the payment to income ratio are computed just by replacing the payment to income ratio X with 0.3, and this is the value of the community density function where Z is equal to minus 1.3. And then when instead the payment to income ratio is equal to 0.4, then this is the value for the probability of being denied. So basically this probability rises from 0.097 to 0.16. And what we can imagine is that, so this is the case of increasing the payment income ratio from 0.3 to 0.4 increases the probability of being denied of this amount. If we instead computed the predicted probability at the payment income ratio equal to 0.6 and 0.65, the effect would be lower. So it's not constant because we are not anymore in the case of a linear model. Okay. This is actually, okay. This is the case, so until now we've seen the case in which we add just one X. Now we are introducing, so we are in the field of multiple regression models. non-linear probability models with multiple regressors, but we have another variable there, and this is whether basically the race of an individual has an effect or does not have an effect. And then the interpretation of our coefficient is basically the same. Okay, so if we want to compute then the predicted value, we need just to compute the predicted value for this variable equal to 1 or equal to 0. So we do the same as before, just for a black or a white person. Okay. Because basically they say that from the data, white people have more access to these loans. So we need to, whether we want to estimate beta 1, so the effect of the payment income ratio to the probability of being denied or not, should be something that controls for whether we have a black or a white person. So we just, whenever we compute the predicted value, we need to be careful on whether this other variable is equal to 1 or equal to 0. Okay, that's why. So here, before we just add this part. Okay, so this was the predicted value of deny equal to 1 when x was equal to 0.3. Now we need to have also value for the other variable, and then here in the definition of z, of course, we have also the coefficient ahead of the estimated ahead of the other variable 0.71. This one times 1 or times 0. Okay, so in the case in which the other variable race was equal to 1, we had 0.71 times 1. The case in which race was equal to 0, we had, of course, 0.71 times 0. Okay, so next time we will start by the logic regression model. We will see differences and also this maximum likelihood estimation method and what changes in terms of estimation and methods. Okay, and then we are done. Questions?